So, welcome to lecture series on advanced linear algebra. See, we have already studied in the inner product space the concept of best approximations of a vector on a subspace of vector space. We have seen if we consider a vector beta in an inner product space V, and if I consider W be a subspace of V, if the best approximation of beta on W exists, say that is alpha, then we have seen that beta minus alpha is orthogonal to each and every element of W. So, this means that beta minus alpha does not belongs to W. So, this motivates us to introduce one more terminology, it is called orthogonal complement. So, what is orthogonal complement? Let V be an inner product space, let W be a subspace, W be a subspace of V. The orthogonal complement of W is a set, is a subset W complement of V such that each element of W complement is orthogonal to every element of W. Every element of W. So, this implies your W bar, I can say that this implies W bar which is subset of V, and W bar W complement is also a subspace of V. So, W complement is a subspace of V, this has to be also prove it. So, for any alpha beta belongs to W bar W complement, and C belongs to the field over which the vector space V is defined, then claim C alpha plus beta also belongs to W complement. So, this will be in W complement provided C alpha plus beta is orthogonal to each element of W. We have for any gamma belongs to W, inner product of C alpha plus beta and gamma which is equal to C inner product of alpha gamma plus inner product of beta gamma. So, since alpha belongs to W complement and orthogonal complement, and gamma or beta also belong to W complement, orthogonal complement basically. So, this means that this is equal to 0 and this is also equal to 0. So, this means that this is equal to 0. So, this implies C alpha plus beta also belongs to W complement. So, we see that if here the orthogonal complement of the subspace W is also a subspace of the vector space V. Let me introduce one more terminology. This is called orthogonal projection. So, let V be an inner product space, and W be a subspace of V. If for beta belongs to V, if the best approximation of beta on W exists, that is, if alpha belongs to W be the best approximation then alpha is called as orthogonal projection of beta. Alpha is called as orthogonal projection of beta on W, where we know that beta minus alpha is orthogonal to each element of W. See, in our last class we have seen if W is finite dimensional, then for each vector beta in V, the best approximation of beta on W exists, and that is also unique, which is having a typical form which is already known to us. Now, if I say that W is may not be finite dimensional, but if for each element of V the best approximation of that element on W exists, then it will introduce a function that is called orthogonal projection of V on W. So, what is that? If for each element of V the best approximation on W exists, if for each element say beta of V, the best approximation say alpha on V exists, then the map which assign each beta to alpha is called as orthogonal projection of V on W. So, orthogonal projection of V on W is a map, is a function from V to W which assign each element of V to its best approximation on W. It is like this: E is a function from V to W is mapping beta to E beta, which is equal to something alpha belongs to W place. So, we have orthogonal projection of a vector V on a subspace W. See, the existence of best approximation will be assured if W is finite dimensional. So, in that case, if W is a finite dimensional, then one can also have a orthogonal projection of V on its orthogonal complement space also, subspace also. So, what I mean to say you, it is in terms of corollary. Let V be an inner product space and W be a finite dimensional subspace of V. Let E be the orthogonal projection of V on W. Then the mapping which assigns each element beta of V into an element beta minus E beta is a function from V into W complement is a, I can say, is an orthogonal projection. Now, projection of V on W complement, I mean orthogonal complement of W, please. So, this can be proved using best approximation and the concept of orthogonal projection. For beta belongs to V, beta minus E beta is orthogonal to each element of W, because E beta is the, since E beta is the best approximation of beta on W. So, according to definition, beta minus E beta is orthogonal to each element of W. So, this implies beta minus E beta will be in W complement. So, this implies the function, say psi, which assign each beta to beta minus E beta is a function from V onto W complement. That is, psi is a function from V to W complement defined by beta psi of beta equal to beta minus A beta. Now, claim is that this function psi, I mean which mapping beta to beta minus E beta is basically orthogonal projection of V on W complement. Claim psi is orthogonal projection of V on W complement. We have to show beta minus E beta is the best approximation of beta on W complement. That is, for any gamma belongs to W complement, I have to show that norm of beta minus gamma will be greater than or equal to norm of beta minus E beta. We have to prove this one, please. We have norm of beta minus gamma whole square equal to, I can write down norm of beta minus E beta plus E beta and minus gamma whole square. So, this is equal to, one can write down E beta and plus beta minus E beta and minus gamma, this whole square. We have beta minus E beta minus gamma belongs to W complement, because beta minus E beta belongs to W complement and gamma also belongs to W complement, and W complement is subspace. So, this implies this beta minus E beta minus gamma belongs to W complement. So, this implies norm of beta minus gamma or whole square using the definition of inner product, then we will have basically what? This will be equal to norm of E beta square plus norm of beta minus E beta minus gamma whole square. So, this implies that norm of beta minus gamma is whole square is greater than or equal to norm of E beta square, because this quantity is positive quantity. Norm of beta minus E beta minus gamma whole square is a positive quantity. Therefore, norm of beta minus gamma whole square will certainly greater than or equal to norm of E beta whole square, please. So, this implies norm of beta minus gamma is greater than or equal to norm of E beta, which is equal to beta minus E beta. So, this implies, okay. So, this is basically our required result, please. Okay. So, beta minus E beta is the best approximation of beta on W complement. So, we see that if V be a inner product space and W is a finite dimensional subspace, then one can have basically orthogonal projection of V on W as well as orthogonal projection of V on orthogonal complement. So, this implies if W is a finite dimensional subspace of inner product space V, then there exists orthogonal projection E of V on W as well as orthogonal projection of V on W complement, orthogonal complement. The way the orthogonal projection psi is defined here, the orthogonal projection psi is basically I minus E, because psi of beta is equal to I minus E operating on beta, that is equal to beta minus. So, we have now seen that if V is an inner product space and W is a finite dimensional subspace of V, then there is a orthogonal projection of V on W as well as on orthogonal complement of W. So, this gives a hint that is it possible to write the space V as a direct sum of two subspaces which are independent to each other. So, these questions can be answered by these theorems. Let V be an inner product space, let W be a finite dimensional subspace of V, let E be the orthogonal projection of V on W. Then E is an idempotent linear transformation from V onto W, that is E square equal to E on W. Second, the null space of E is W complement, that is orthogonal complement of W. Third, V is equal to direct sum of W and W complement, where W intersection W complement equal to 0 subspace. So, let me prove one by one this result please. So, it is given E is an orthogonal projection of V on W. So, this implies E maps to any element beta belongs to V to E beta. Beta minus E beta is orthogonal to each element of W. Each element of this means E beta is the best approximation of beta on W. So, this implies if beta belongs to W, then certainly E beta will be equal to beta, so that the best approximation of beta on W will be itself basically. Okay. So, in this case, when you consider E operating on again E beta, that is equal to E beta. So, this implies that E square beta equal to E beta. This is true for all beta belongs to W. So, this implies E square equal to E. So, this implies E is an idempotent linear transformation from V onto W. So, this is the first part of this results. Second, if E of beta equal to 0, this implies that beta minus E of beta, which is equal to beta, is in W complement. So, this implies that beta belongs to, so this implies E beta equal to 0 implies beta belongs to the null space of beta. So, this implies any element of the null space of E is also an element of W complement. Again, if beta belongs to W complement, then this implies the E beta will be equal to 0, because the best approximations of beta on W will be 0. So, this implies E beta equal to 0. So, this implies beta belongs to null space of E. So, null space of E equal to W complement. Third, for this is third one, this is my second and the first one. Okay. Okay. For third one, that I have to show that V is the direct sum of W and W complement. For this, for any beta belongs to V, we have beta equal to E beta plus beta minus E beta. One can write down beta is equal to like this. So, this implies E beta belongs to W and beta minus E beta belongs to W complement. So, we see that beta can be written as the sum of element from the W and sum of as well as element of the W complement place. So, this implies beta can be written as sum of element from W as well as element from your W complement. So, it has two components, one component from W, another component from the W complement. It will be direct sum provided if I can somehow show that W and W complement, they are mutually disjoints. So, now I want to show W intersection W complement equal to 0 subspace. Suppose not, if 0 not equal to alpha belongs to W intersection W complement. So, this implies inner product of alpha and alpha equal to 0, since alpha belongs to W and so this implies alpha is orthogonal complement of itself. So, this implies inner product of alpha and alpha equal to 0. This is possible only when alpha equal to 0. So, this implies that W intersection W complement equal to 0 subspace. So, now we have seen that if V is an inner product space and W is a finite dimensional subspace, then V can be written as direct sum of W and its corresponding orthogonal complement. So, this given hints and also one interesting results, that is called Bessel's inequality. What is that? Let V be an inner product space let alpha 1, alpha 2, alpha n be a set of non-zero orthogonal vectors of V. Let beta belongs to V be any element, then sigma absolute value of inner product of beta alpha k square by norm of alpha k square k equal to 1 to n, this quantity will be less than equal to norm of beta square. This is called the Bessel's inequality. Bessel's inequality. This is also coming as a consequence of very straightforward results what we have already explained. How? Proof is again straightforward. Let W be a subspace of V spanned by your given orthogonal vectors alpha 1 to alpha n. So, this implies W is a finite dimensional subspace of V. This implies V can be written as direct sum of W and W complement. So, this implies for any element beta belongs to V, I will have beta is equal to something like beta 1 plus beta 2, where beta 1 is coming from W and beta 2 coming from W complement. Now, what is beta 1? Beta 1 is basically the best approximation of beta on W. Here beta 1 is basically best approximation of beta on W, because W is a finite dimensional. So, best approximation of beta on W exists and it is unique, which is also unique. So, this implies one can write down beta 1 is equal to sigma inner product of beta and alpha k divided by norm of alpha k square into alpha k, k equal to 1 to n. So, I can have beta 1 is like this thing, this is the best approximation of beta on W. So, this implies that beta 1 is orthogonal to beta 2 also. Now, norm of beta square is equal to norm of beta 1 plus beta 2 square. So, this is equal to basically norm of beta 1 square plus norm of beta 2 square. Since inner product of beta 1 and beta 2 equal to 0. So, I have norm of beta square equal to like this. Beta 1 square is nothing inner product of sigma beta alpha k by norm of alpha k square and alpha k and sigma beta alpha j suppose by norm of alpha j square and alpha j. For sake of simplicity only I have changed the suffix, so that it will not confuse us that why we have written same alpha j. So, I can say j equal to 1 to n, k equal to 1 to n. So, if I use the basic definition of inner product, then this is going to, and use the orthogonality nature of alpha I. So, this will give me basically your sigma a mod of beta and alpha k square by norm of alpha k square only, k equal to 1 to n. You can check as a homework that this is correct. This implies norm of beta square is equal to sigma inner product of beta and alpha k square by norm of alpha k square, k equal to 1 to n plus your norm of beta 2 square. Okay. So, this quantity is also positive quantity. So, this implies norm of k equal to 1 to n mod of beta and alpha k square by norm of alpha k square will be less than equal to norm of beta square. Okay. So, one may ask the question, under what condition equality will holds good. So, as a note I can say, if dimension of B is finite and n, then norm of beta square will be exactly equal to k equal to 1 to n inner product of beta alpha k square by this alpha k square. So, friends, we see that this concept of orthogonal projections gives so nice results on the inner product space. It split the space into direct sum of two subspaces, and it also talk about the best approximations of a vector in V with respect to subspace W, and the concept of orthogonal projections will be useful in our next lectures, in coming lectures. So, we will see that this concept will be useful in different angle phase. So, we will discuss more on this issue as an assignment problems. So, I hope you have understood the concept of orthogonal projections on a inner product space. Next class talks about the linear functionals and inner products and their relation, please.